Please check my research. It is for 9.5 years of torture. Our GPS can collect quantum video and audio from inside anyone's home. Don't believe me? Check my research. The only thing you will lose is 30 MIN, but that isn't much to get the biggest story you and everyone in your office will see in your lifetime. GPS is a supercomputer that is very much against our constitutional rights and is being taught to our military. WHO intern use it for neighborhood watch. Illegal much. Police and every government department that we have contacted response when we ask for help. That's not our department. Really? FCC, DOD. 3 generators, 3 diode NM lasers. How GPS and GPS satellites are part of a quantum nanoparticle optic supercomputer system to look and listen into anyone's home and or private property. GPS is made up of signals. The ones that I will be focusing on are L1 1575.42 MHz, L1 1575.42 is also a GHz and is a microwave signal, and C, A code 1.023 MHz. These are radio signals. They carry radio frequencies. There are 4 signals available for civilian use. In order of date of introduction, these are L1C, A, L2C, L5 and L1C. L1C, A, these are carrier signals that can carry IP addresses and frequencies, also called the legacy signal, and is broadcast by all satellites. The other signals are called modernized signals and are not broadcast by all satellites. In addition, there are restricted signals with published frequencies and chip rates but encrypted coding intended to be used only by authorized parties. Some limited use of restricted signals can still be made by civilians without decryption. This is called codeless and semi-codeless access and is officially supported. Let me give you the definition of a radio frequency and we will go from there. Radio frequencies. The radio spectrum is the radio frequency, RF portion of the electromagnetic spectrum. In the United States, regulatory responsibility for the radio spectrum is divided between the Federal Communications Commission, FCC, and the National Telecommunications and Information Administration, NTIA. The FCC, which is an independent regulatory agency, administers spectrum for non-federal use, i.e., state, local government, commercial, private, internal business, and personal use, and the NTIA, which is an operating unit of the Department of Commerce, administers spectrum for federal use, e.g., used by the Army, the FAA, and the FBI. Within the FCC, the Office of Engineering and Technology, OET, provides advice on technical and policy issues pertaining to spectrum allocation and use. 1-3GENERATORSTHESENEXT6SYSTEMS of the Foundation for Quantum Optics Supercomputer BASICLLY, a vapor computer. Asterisk GPS generator. C, A code of the GPS can have IP addresses and frequency into the L1 1575.42 MHz, able to become part of the phase-locked loop and get into voting booths in computers. Now sent to the L1 1575.42 MHz. Asterisk rubidium atomic clock terahertz. Rubidium atoms, BAPORB, are the building blocks for control of GPS signal with standard frequency time signal for in quantum optics computing. These items make up a rubidium-filled digital optical microwave phase-locked loop. An optical frequency comb tied to GPS for laser frequency, wavelength calibration. https://www.ncbi.nlm.ni.gov/pmc/articles/pmc4548864/ Asterisk digital optical frequency comb. 4-6 LASERS. 780 nm, adjustable, so if you see different nm digits, these are adjustable. Signal laser, excites rubidium electrons. 1550 nm, adjustable, infrared probe laser, part 1 of a 2-part laser system to create Doppler cooling on rubidium atoms. Also a C-band. C-band is a nanopolymer, polymer equals laser for collecting and recording data. Audio, video. 1560 nm. Laser system to create Doppler cooling on rubidium atoms. Also a C-band, nanopolymer. Quantum radio. https://military-embedded.com/com/cognitive-radio/quantum-within-harsh-environments. https://u2.b/3zdgmhxc5ra. All of the above items create a digital optic microwave phase-locked loop DOMPLL. This makes the containment unit for a quantum optic nanoparticles supercomputer which can go around anyone's home, building, and voting booth and is mostly made of microwaves. It also produces a quantum optic nanoparticles two-way radio. The digital optic microwave phase-locked loop is created partly from our GPS system, meaning it can target anyone or any place in the world. On Earth. terahertz THZ plus rubidium plus THZ glasses equals T-ray vision, same as at an airport. OR it can be produced with quantum optics absorption electromagnetic radiant energy. Now how video, audio and much more is extracted from our home or any home when surrounded by a digital microwave optical phase locked loop. We will be taking a look at electronically induced transparency and absorption, 1550 nm laser probe, and 1560 coupling. Creating Doppler cooling of RB from 186,000 miles per sec to 32 miles per hour. Let's get started. Rubidium atoms are held in place by digital optical phase locked loop, Zeeman effect and optic lasers, 1550 nm probe, 1560 coupling, creating Doppler cooling. The 780 nm signal excites the rubidium atom's electron into a higher than normal orbit. This electron can absorb electromagnetic radiant energy, radio waves, microwaves, infrared, visible, light, ultraviolet, X-rays, T-rays, and gamma rays. When the electron loses its energy, it produces photons, one bright and one dark. This is where we get started with quantum computing. The photons are then released and takes with it all information, radiant energy information, absorbed by the excited RB electron. Radio waves, microwaves, infrared, visible, light, ultraviolet, X-rays, and gamma rays are transferred into a rubidium photon and then onto the C-band nanopolymer coupling laser, which carries all information happening in the GPS, rubidium, frequency comb, digital, microwave, optical, phase locked loop and sends it out to be decoded with proper equipment. Sharing all info in DMOPLL, video, audio, etc. anywhere in the world via C-band. An optical DPSK demodulator is a device that provides a method for converting an optical differential phase shift keying DPSK signal to an intensity keyed signal at the receiving end in fiber optic communication networks. It is also known as delay line interferometer (DLI) or simply called DPSK demodulator. Now let's backtrack a bit to the CA code and how IP addresses can be inserted for computer hacking. Here is a link that explains how it is done. It basically turns your IP address into ones and zeros. Computer talk can be added to CA code using bit codes zeros and ones with BPSK modulation method. Then it joins L1 1575.42 MHz, which is a microwave signal carrier which will become part of the optic microwave phase locked loop. How conversion is done from IP to binary. https://petri.com/csc_convert_from_decimal_to_binary hash : #text equals here %20 or %20 steps %20 on %20 how, it's %20 binary %20 form %2c %20 without %20 memorization. And text equals in %20 order %20 to %20 remember %20 these, 1 %20 x %202 %20 3d %202 closing parenthesis. Ping is used to gain access to any GPS or satellite equipment in vehicle, and it can be used on any electronics in the optic phase locked loop. Let that set in. Pinging a new known and unknown host port and IP address will generate DNS packets. For any new known and unknown host port and IP address, it will generate at least 2 packets like request and reply model, and a maximum 27 packets we can generate per ping request. A ping can be sent to you satellite radio, and poof, a DMOPLL can be produced around your car. Now the information is ready to be shared via satellite or 5G. Imagine this phase locked loop over an electronic voting station. Computers speak in ones and zeros called binary code. Person puts binary turned bit code information into CA code 1.023 MHz, which then goes to L1 1575.42, becomes part of the phase locked loop. Radio frequency over fiber, laser ROF, also becoming a part of a quantum optics computer with the ability to hack whatever is in the phase locked loop. Electronic voting booths. 3 and 3 surveillance, weapon GPS, rubidium atomic clock, optic frequency comb, able to put optical phase locked loop around a home, voting booth building. All of these things can be produced from a THZ GPS satellite and are responsible for 3 main weapon systems that are created with this quantum optics THZ, GPS, rubidium, quantum optics computer. Voice of God in China 2. https://u2.be/cpqx1acback. Inside of this digital optic microwave phase locked loop DOMPLL are microwaves from carrier signals and terahertz and more, which are contained in an electromagnetic optical phase locked loop EOPLL, which can be controlled with GPS and rubidium atomic clock standard frequency time signal. Check my research. When the EOPLL is put around a target, that target is saturated with microwaves, and this causes the frontal lobe of the brain and the cochlea to swell, letting radio frequencies bypass the ear canal and eardrum, bouncing off the cochlea and onto the frontal lobe, producing sound like a cochlea implant. This is called microwave auditory effect hearing. The radio frequencies are added to the CA code 1.023 MHz on the GPS becoming 1, then moves to be joined with L1 1575.42 MHz and sent out to be wrapped around the frequency comb lasers. This is called radio frequencies over fiber. Now remember, the EOPLL is made up of all of this, so consider it a dome of radio frequencies for now. The added frequencies can now be dialed up with SDR, radio phones, or any two-way radio like a police would use, and more than one frequency can be attached to the equals multiple audio signals, hearing voices, harassment, terrorists. Here are the diplomats. Cricket noise. Microwave auditory effect hearing. Sonic health attacks are brought on the same way, but what is heard here are the superposition beat frequencies. The cricket noise basically hear multiple frequencies of different lengths. Phase detector. Low pass filter. Voltage controlled oscillator, and feedback path, which may include a frequency divider. The voltage-controlled oscillator increases and decreases the DC current. The higher the current, the higher the frequency, and the lower the current, the lower the frequency. Here is a video link. Sonic Health Attack 3. https://u2.be/kgshhjgvjgq. Terahertz Image 4. https://www.rp-photonics.com/terahertz_radiation.html. Types of phase locked loops 5. https://www.jins.com/americas/applications/optics-photonics/optical-phase-locked-loops. Now to back my claims, here is the technical side of what I am claiming. Volume 112 2007, Actaphysica POLONICAA No. 5. Proceedings of the International School and Conference on Optics in Optical Materials, ISCOM 07, Belgrade, Serbia, September 3-7, 2007. Dark Resonances in Quantum Optics. E. Aramondo. CNRINFM and CNISM, Departamento di Fisica E. Fermi. Università di Pisa, Largo Pontecorvo 3, Pisa, Italy. The processes occurring in three-level systems are briefly reviewed. Coherent population trapping, bright resonances, electromagnetic induced transparency, electromagnetic induced transparency, optical clock or DIS. CUST. PAX numbers 42.50. GY. 1. Introduction. Quantum control and quantum computation, representing two important directions of today. Research rely on the precise modification of quantum mechan. ICAL systems not perturbed by an environment presence. This precise control was reached in different areas of physics using electromagnetic fields interacting with atoms or molecules in different matter phases. The simplest quantum mechanical system to be explored is a two-level atom with lower and upper levels excited by a resonant or quasi-resonant electromagnetic field, as it occurs in nuclear or electronic magnetic resonance or in two-level laser spectroscopy. They're the populations of the two levels, or the coherence between the two levels, are precisely modified by a control on the frequency, amplitude and interaction time of the electromagnetic field. The weak perturbation by the environment is realized. For instance, operating with low pressure or with cold, ultra-cold gases is produced by the combination of laser cooling and evaporative cooling techniques. The next step in level complexity is the three-level systems with three levels, to be denoted as 0I pi, C, excited by two separate lasers, the first probe laser at frequency omega p driving the transition pi 0I, and the coupling laser at frequency omega c driving the transition c 0I. The atom laser interaction of a three-level system is based on the evolution of the population of the three levels of the optical coherences between levels 0I pi and 0I c. In addition, the three-level system may be prepared by the applied lasers in a coherent superposition state, whence it supports one high-order coherence between levels pi and c. The build up of that coherence by the applied lasers produces new processes and new phi-like phenomena peculiar of the three-level configuration. Those processes and phenomena have stimulated a large attention by the laser spectroscopy and quantum optics. 723 Fig. 1. A lambda scheme with lower levels 1I and 2I and upper level 3I. Applying the probe laser and the coupling laser, a coherence is established between the lower levels, mediated by the upper 1B3 level 88 senior configuration for an optical clock. Communities in the last 30 years, as presented in 1 to 4. The three-level On upper level, 0I separated by an energy splitting in the optical range as schemat. Ically represented in Fig. 1a constitutes the most interesting configuration. In fact, the time evolution of the high-order coherence is not limited by the spontaneous emission processes from the upper level and takes place on a timescale much slower than the optical oscillation time. Therefore, the phenomena of dark resonances DR, coherent population trapping, CPT, electromagnetic induced transparency, EIT, are greatly enhanced in the lambda system. When an atomic system is prepared in a coherent superposition state, very narrow resonances can be observed where the presence of the atomic coherence cancels or reduces absorption and greatly modifies the refractive index of the medium. The early study relevant to this situation includes measurement performed in Pisa and Rochester, where terms such as dark resonance and CPT were introduced 5 to 7. The continually expanding interest in the topic is due not only to the fascinating physics involving quantum coherence but also to the fact that there are many potential applications with relevance both in possible implementation of new techniques and devices and in new scientific research approaches to fundamental studies such as slowing of light, nonlinear optics, quantum information storage, frequency standards, precise magnetometers, and some more. Section 2 of the present work introduces the basic concepts of the three-level phenomena. Sect 3 discusses the proposed EIT application to the 88th senior optical clock. 2. Basic. The three-level system considered here is shown in Fig. 1a. The energy separation between levels E and G denoted as H omega ij. The common level, 0I, is coupled to both levels pi and C through transitions induced by two applied classical laser fields, probe, and coupling lasers, respectively. It is supposed that, either due to selection rules produced by a proper choice of the polarizations of dark resonances in quantum optics 725, the two laser fields, or because of properly chosen frequency detunings, each laser field acts only on one transition. The laser detunings are delta P equals omega P minus omega 0 P and delta C equals omega C minus omega 0 C, and the Raman detuning is equals delta P minus delta C. The Rabi frequencies omega P and omega C characterize the atom laser interaction. The main relaxation processes completing the three-level evolution are the spontaneous decay from upper level 0I with total rate gamma and the decay rate gamma Cp of the second-order coherence between levels pi and C. Very peculiar narrow features appear for the occupation of the 0I upper level when the two-photon condition is satisfied, i.e. around the two-photon Raman resonance condition 0. Figure 2, left part, shows numerical results for the line shape of the Wobbs absorption for the probe laser, and that line shape is identical to line shape of the 0I level population. The coupling laser is fixed at its Fig. 2. Left, absorption rate of the 461 nm laser in the lambda optical clock scheme of 88 senior in the presence of the 1354 nm control laser. Right, chi. 0. Susceptibility of the 461 nm laser in the 88 senior lambda scheme. Laser parameters delta C equals 0, omega C equals 10 minus 6 gamma. The insets show, on an expanded scale, the central EIT features. Resonance value delta C equals 0, whereas the probe laser is swept around its optical resonance when the two laser fields are scanned around the Raman resonance values. The probe absorption and the population of the upper 0I level increases following the Lorentzian profile of the absorption line. A maximum of both quantities is expected with both lasers in resonance. However, a strong decrease occurs in a narrow region around the Raman resonance where the atoms remain distributed over the lower 1I and 2I levels without occupation of the upper level. The population of the lambda system is trapped in the lower states. The fluorescent emission from the upper level, which is proportional to the excited level occupation, presents a strong decrease at the Raman resonance value. The decrease denoted as dark line. In the experimental observations of 5 away from the Raman resonance, the occupation of the three levels is determined by the optical pumping process. Because of the optical pumping redistribution among the three levels, the CPT results do not depend on the initial level populations. Similar results for the absorption and excited state population line shape are obtained with the coupling laser fixed at a value not corresponding to the optical resonance delta C6 equals 0 and scanning the frequency of the probe laser around the resonance Raman condition equals 0. CPT is again produced with a drastic decrease in the probe absorption and in the excited state. Population. If we disregard gamma CP for a moment, the absorption rate vanishes exactly. At equals 0, evidence of the EIT effect 1. The occurrence of a zero in the absorption profile is clear from the connection of this problem to the Fano 8-9 line shape. With an asymmetry produced by interference between different probe absorption processes, the EIT deep, narrow dip occurring in the absorption profile presents a width determined by gamma CP and the absorption rate gamma equals omega 2 C gamma. A unitary transformation is very useful for understanding the CPT process. Let us analyze the simple case in which the two lower levels pi and c are degenerate and the two laser fields have the same frequency and phase. We may introduce the dark or non-coupled psi and ci and bright or coupled states psi c2. Describe the atomic evolution between the lower levels. Psi and ci equals q omega c omega 2 p plus omega 2 c pi minus q omega p omega 2 p plus omega 2 c c1 psi c equals q omega p omega 2 p plus omega 2 c pi minus q omega c omega 2 p plus omega 2 c c2. Because the transition matrix element between nci and 0i vanishes, an atom in that state cannot absorb photon and be excited to 0i. Atoms are pumped into psi and ci after a few spontaneous emission cycles. Numerical results for the EIT narrow dip in the absorption profile are shown in the left part of Fig. 2 for the case of the lambda configuration introduced in Sect. 3. The EIT process, characterized by a decreased absorption, is described by the absorption length zeta EIT p, defining the exponential decay of the probe in the propagation zeta EIT p equals zeta p omega 2 c 2 gamma cp gamma plus 1 3, where zeta p denotes the probe Beer absorption length in the absence of coupling laser. Equation 3 predicts no probe attenuation for the case of gamma cp equals 0. The EIT narrow modification of the atomic response appears also in the real part of the optical susceptibility chi 0 omega p that determines the refractive index and the light propagation speed within the medium. The EIT modification of the refractive index with a narrow and inverted dispersion line shape is shown in the right part of Fig. 2. The group velocity Vg characterizing the propagation of a laser pulse through the EIT medium is given by Vg equals c 1 plus chi 0 omega p 2 plus omega p 2 chi 0 omega p dot 4. The EIT narrow dispersion peak produces slow light propagating through the in the field of optical frequency standards, alkaline earth atoms or ions are attractive candidates for new clock performances where resonance quality factors are expected to be better than microwave-based atomic clocks. A competitive proposal is to localize neutral cold atoms spatially in a lambdic regime while the trapping potential is designed such that its presence does not influence the clock transition frequency. This scheme can be realized using a far-off resonance dipole trap operating at a wavelength where the ground and the excited state of the clock transition experience exactly the same AC Stark shifts. A state with a scalar polarizability is preferred to avoid the problem of the complex and sometimes uncontrolled light polarization inside an optical lattice. In 9, a scheme of an optical clock based on states of true scalar nature, namely 5s. 21SO minus 5s 5p. 3PO of 88 senior with I equals 0 was proposed. A direct transition between these two states is of course completely forbidden, and the clock scheme is based instead on 3-level quantum coherence established by 2 probe laser frequencies. In the 88 senior lambda, since the ground state 5s 21SO, state pi, and the first excited state 5s 5p. 3PO, state c, of 88 senior are characterized by a total angular momentum of J equals 0, electric and magnetic 1 photon transition matrix elements between these two states vanish to any multipole order. The 5s 5p, 1p1 state 0i, can be reached from pi via E1 1 photon absorption using the probe laser at a wavelength of 461 nm. 1m1 photon from the coupling laser at 1354 nm is needed to resonantly couple C and 0i. The latter decays primarily to pi with gamma 0p equals 2 pi 32 mhz. If the dressing laser is off the Lorentzian profile connected with the pi 0i, transition is recovered. Otherwise, the absorption rate vanishes at equals 0 as for EIT. For the narrow EIT dip occurring in the absorption profile, not only its position, but also its width is very insensitive with respect to fluctuations of delta C. A variation of the dressing laser frequency by as much as 100 kHz induces a relative change of the EIT width of less than 10⁻⁷. By measuring the absorption as a function of omega p minus omega c, the clock frequency can be determined with high accuracy by tracking the position of the dip. Neither omega p nor omega c must be particularly stable. Only the difference needs to be stabilized. For relatively large detuning, delta c equals 5 gamma. The signal amplitude is reduced and the peak disappears as soon as decoherence becomes appreciable. In order to evaluate the potential accuracy of the proposed clock scheme, the AC Stark shifts due to non-resonant electric dipole coupling of the three levels to states inside and outside the three-level subspace should be considered. These AC shifts may be controlled by operating the clock at very low Rabi frequencies. However, this simple approach does not apply to EIT clocks where the laser intensity modifies also the optical pumping time to prepare atoms into coherent superposi. On characterizing the EIT response for. To overcome these limits, refs 10, 11. Examined a scheme based on the interaction of the atomic clock transition with time-separated Raman laser pulses Fig. 3. Moreover, the detunings of the applied in the field of optical frequency standards, alkaline earth atoms or ions are attractive candidates for new clock performances where resonance quality factors are expected to be better than microwave-based atomic clocks. A competitive proposal is to localize neutral cold atoms spatially in a lambdic regime while the trapping potential is designed such that its presence does not influence the clock transition frequency. This scheme can be realized using a far-off resonance dipole trap operating at a wavelength where the ground and the excited state of the clock transition experience exactly the same AC Stark shifts. A state with a scalar polarizability is preferred to avoid the problem of the complex and sometimes uncontrolled light polarization inside an optical lattice. In 9, a scheme of an optical clock based on states of true scalar nature, namely 5s. 2 1 SO minus 5s 5p. 3PO of 88 senior with I equals 0 was proposed. A direct transition between these two states is of course completely forbidden, and the clock scheme is based instead on three-level quantum coherence established by two probe laser frequencies. In the 88 senior lambda, since the ground state 5s 2 1 SO, state pi, and the first excited state 5s 5p. 3PO, state C, of 88 senior are characterized by a total angular momentum of J equals 0, electric and magnetic one-photon transition matrix elements between these two states vanish to any multipole order. The 5s 5p, 1p1 state 0i, can be reached from pi via E1 one-photon absorption using the probe laser at a wavelength of 461 nm. 1m one-photon from the coupling laser at 1354 nm is needed to resonantly couple C and 0i. The latter decays primarily to pi with gamma 0p equals 2 pi 32 mHz. If the dressing laser is off the Lorentzian profile connected with the pi 0i, transition is recovered. Otherwise, the absorption rate vanishes at equals 0 as for EIT. For the narrow EIT dip occurring in the absorption profile, not only its position, but also its width is very insensitive with respect to fluctuations of delta C. A variation of the dressing laser frequency by as much as 100 kHz induces a relative change of the EIT width of less than 10⁻⁷. By measuring the absorption as a function of omega p minus omega c, the clock frequency can be determined with high accuracy by tracking the position of the dip. Neither omega p nor omega c must be particularly stable. Only the difference needs to be stabilized. For relatively large detuning, delta c equals 5 gamma. The signal amplitude is reduced and the peak disappears as soon as decoherence becomes appreciable. In order to evaluate the potential accuracy of the proposed clock scheme, the AC Stark shifts due to non-resonant electric dipole coupling of the three levels to states inside and outside the three-level subspace should be considered. These AC shifts may be controlled by operating the clock at very low Rabi frequencies. However, this simple approach does not apply to EIT clocks where the laser intensity modifies also the optical pumping time to prepare atoms into coherent superposi. T on characterizing the EIT response 4. To overcome these limits, refs. 10, 11. Examined a scheme based on the interaction of the atomic clock transition with time-separated Raman laser pulses Fig. 3. Moreover, the detunings of the applied 28E. Aramondo. Fig. 3. The Ramsey pulse sequence probes the EIT resonance. EIT preparation takes place during the tau window. After AT interval of free evolution, the EIT is interrogated. During tau M with a later detection of the ground state occupation, lasers change the phase evolution of the atomic wave function so that a proper combination of magic, laser detuning and pulse duration allows to compensate for the AC Stark shifts. In addition, the pulsed configuration produces a large contrast in the detected clock signal. This interrogation scheme represents an original mix of the Ramsey phase spectroscopy and high-efficient population transfer under CPT acting as a quantum non-demolition measurement. This method performs the 10 mHz accuracy expected for a light-insensitive lattice clock with Ramsey EIT pulses to dilute fluctuations of the frequency resolution over probing time. Tau plus T plus tau M. The pulse approach remains valid for multi-photon excitation paths, where dark states can be found as a clock transition. Acknowledgements. This work was supported by the OLAQUI and EMILY European projects, and by MIUR Italy PRIN contracts. The senior optical clock is based on a collabo ration with C. Green, R. Santra, Jun Yi and T. San and Willett.